every star and galaxy, was born out of a singularity that brought about our whole existence. The Big Bang, an isolated moment in space and time, created something out of nothing. For eons we didn't know much about the universe, but through advancements in science and technology, we're now able to travel back in time, right to the point just after the Big Bang to finally piece together its entire story. And in the next 10 minutes, I'll be sharing that story with you. To be able to understand the history of our universe, we have to start at the beginning of time, and time itself was born with the Big Bang. Contrary to what its name might suggest, the Big Bang was not an explosion. It can more precisely be described as the rapid expansion of space and time in all directions, releasing immense amounts of radiation. In 1964, two Americans, astronomer Robert Wilson and astrophysicist Arno Penzias, stumbled upon a cryptic message traveling from the moment of creation itself. Their antenna in New Jersey picked up an odd buzzing sound that puzzled them. After eliminating all possible sources of interference, Wilson and Penzias figured out that they had just discovered the cosmic microwave background, or CMB, the thermal echo of the universe's explosive birth, and the most crucial piece of evidence for the Big Bang. Thanks to this ancient message, we know our universe came into existence 13.7 billion years ago, and it immediately began expanding at an exponential rate. This is known as the inflation epoch. When it was less than a blink of an eye old, like a billionth of a trillionth of a second old, our universe underwent an astounding growth spurt faster than the speed of light. Within a fraction of a second, it doubled in size at least 90 times. But as it expanded, the energy released became more diluted. In just 3 minutes, the universe had cooled down enough to allow the first particles of matter to form, and the first light elements were created. Neutrons and protons began colliding with each other and formed hydrogen, helium, and lithium. Though the particles were formed, the intense heat from the moment of creation made it too hot for light to shine, and so our universe was plunged into a cosmic dark age for hundreds of millions of years. Space was desolate and devoid of any planets, galaxies, or stars. Then the age of re-ionization began, and light finally emerged from the darkness with the birth of the universe's first stars, known as population 3 stars. These are believed to be made of the only ingredients available in the universe at the time: hydrogen, helium, and lithium. These stars are time capsules rich with information about our universe's earliest days, and with the James Webb Space Telescope, we can now look into them with greater detail than ever before. About 1 billion years after the Big Bang, galaxies began to appear, and there are two theories on how they first came into existence. The first suggests that big clouds of gas and dust collapsed under their own gravitational pull, allowing stars to form and eventually galaxies. The second, which has gained momentum in recent years, suggests that galaxies formed when small lumps of matter kept clumping and swirling together until they eventually grew to the size we're familiar with today. Our galaxy, the Milky Way, is roughly 13.6 billion years old and contains between 100 to 400 billion stars, and spans about 100,000 light years across. Astronomers are still working on charting the spiral structure of our galaxy. Although using infrared images from NASA's Spitzer Space Telescope, we've discovered that it is dominated by two arms wrapping off the ends of a central band of stars. Stars and galaxies are still being created to this day, and astronomers estimate that there could be as many as 2 trillion galaxies spiraling through the black ocean of our universe. 4.5 billion years ago, a dense cloud of interstellar gas and dust kept swirling together. As gravity pulled more and more material into the center, the pressure in the core was so great that hydrogen atoms began to form to make helium, releasing immense amounts of energy. This process eventually gave birth to the star we see every morning when we wake up, our sun. Once the sun was formed, the matter surrounding it clustered into spheres and fell into its gravitational pull, creating the planets in our solar system. The giant planets, Jupiter, Saturn, Uranus, and Neptune, were the first to circle the sun. As it began emitting its light, the smaller planets Mercury, Venus, Mars, and our very own Earth formed. Our planet just happened to orbit the sun in what scientists call the Goldilocks zone, the perfect temperature and distance from the sun to allow for liquid water to exist. Somewhere between 60 to 175 million years after our solar system was born, a Mars-sized planet collided with Earth, and the post-impact debris morphed together to give us our moon. Talk about upcycling. Life in our universe seems to be far from inevitable. Everywhere we point our telescopes end up seeing the same thing: bright nebulae, star clusters, and ominous galaxies that all look desolate and lifeless. But when it comes to our home planet, the story is very different. Life on Earth first appeared 3.7 billion years ago, but how it sprung into existence is still a hot topic of debate. Many believe the first living organisms were microscopic microbes that left signals of their presence in rocks. Others think life started in a primordial soup deep in the ocean through vents in the seabeds, where the interaction between water and rocks provided enough chemical energy to allow the first unicellular organisms to emerge. Whichever side of the argument you're on, though, the one thing that's certain is that the Earth was teeming with life long before we showed up. We came onto the cosmic scene just around 6 million years ago. A long time for sure, but minuscule when compared to the 13.7 billion year lifespan of the universe. Although our early ancestors joined the party late, we've moved quicker than we could have ever imagined. In just a short span of time, we've gone from hunter-gatherers to cosmic explorers preparing to create a base on the moon's surface. Our telescopes now allow us to see further than we've ever been able to before, and our questions are bigger than we've ever dared to ask. But even with all the tools available to us, there are things in the universe that are still shrouded in mystery. Around 85% of our universe is made up of a mysterious substance that we have never seen. In 1933, Swiss astronomer Fritz Zwicky measured the visible mass of a cluster of galaxies and found that it was too small to prevent these galaxies from escaping the gravitational pull of the cluster. Zwicky concluded that something must be acting like glue holding the cluster together. That mysterious substance we now describe as dark matter, a completely invisible material that fills up our universe and acts as an astronomically potent superglue. Without dark matter, the behavior of stars, planets, and galaxies would just not make sense, and our universe would not have evolved the way it has. And then there's dark energy, the strange force that is pulling our universe apart at an ever-increasing speed. Just like dark matter, dark energy is invisible, but its powerful effects are largely felt.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In 1920, Edwin Hubble discovered that the universe is not static, but is still expanding. And in 1998, the telescope named after the astronomer proved him right. And even more, that the universe was expanding at an accelerated rate. We have since discovered that dark energy is the reason for this expansion, and also why stars and galaxies recede away from each other. While much about the formation of the universe and its evolution has been theorized and plotted on the cosmic timeline, there are still enduring questions to be answered. With telescopes like Webb, we'll continue to hunt for the elusive dark matter, as well as look back into our universe to understand the evolution of stars and the formation of galaxies. Our quest also includes searching the cosmos in hopes of finding life forms to share our existence with. During this search, we've discovered exoplanets that orbit around a star outside of our solar system. Based on NASA's Kepler Space Telescope imagery, we can confidently assume that every star in the universe has at least one planet orbiting around it. In our galaxy of hundreds of billions of stars, it's believed that there are trillions of exoplanets. Yet we've only discovered around 3,900 of them. A little more than 4 light-years away, Proxima Centauri is the closest of these exoplanets, but scientists have their eyes on bigger things with the TRAPPIST-1 star system. This star system is home to 7 planets, all roughly the size of Earth, orbiting around a red dwarf around 40 light-years away. Our space telescopes, ground telescopes, and best scientists are working to try and understand whether any of these planets have the right ingredients for life to spring into existence. I made an entire video on what it would be like to live on one of these planets, the only one that scientists believe could possibly hold life. Whether we succeed in this mission is a story that will be written in the universe's future. One that will either propel us forward towards the understanding of the cosmos and our place in it, or will leave us pondering our lonely existence. Our universe is currently 93 billion light-years wide, filled with trillions of galaxies, and 1 septillion stars, that's 24 zeros, and it's still expanding through the vastness of space. Sometime in the distant future, it's estimated that our Milky Way will collide with the neighboring Andromeda galaxy. Because though the universe is expanding, galaxies are receding away from each other, and the proximity of the 2 galaxies will make their collision inevitable. Don't worry though, we'll be long gone before that happens. 100 billion years into the future, galaxies will disappear, and eventually, our universe will be populated by black holes ravenously eating away all that is in their way. As a new dark age sets upon our universe, astronomers believe that its fate is bound to end the same way that it began. With time, space will begin contracting again. The universe will shrink in size until one day, it devolves back into the singularity that started it all. A sort of big crunch reversal that'll bring things full circle and leave behind an emptiness aching to be filled. And then, who knows? Bang. Like most children, you go to bed early. In the evening, no later. As your mother tucks you in, you see the warm glow of the sunset hitting your ceiling. The soft reds and the pinks of twilight playing on your bedroom walls. Then, as you've seen her do every night, you watch as she closes the thick black curtains, plunging you into sudden, silky darkness. When you wake up several hours later, calm and refreshed, you throw open the blinds. As usual, it's just as dim as when you went to bed. You see the twilight glow, and again it's soft reds and pinks, playing on your bedroom wall. You run outside to find your mother in the front yard. "Hello, Mom," you scream as you run to meet her. But then you remember her teaching you to say good morning when you wake up, so you do that instead, even though you've never really understood her stories about mornings and evenings in a place where the sky isn't always twilight. To you, this is all there ever was. The sun always hangs in the west, on the horizon, exactly where it is before you sleep and throughout the rest of the day that follows. There have always been not one, not two, but 6 crescent moons strewn across the sky, and the weeds in your front yard have always been jet black. This is all you've ever known. This is life as a human born on another planet. A mere 40 light years from Earth, there's a dim red star called TRAPPIST-1 that hosts 7 rocky planets. Only they've been pulled together so tightly that they don't rotate anymore, so they no longer experience days or nights as we know them. The 4th planet from this star, which astronomers call TRAPPIST-1e, is suspected to have a sliver of landmass that might be habitable to humans. You see, because the planet doesn't rotate anymore, TRAPPIST-1e is effectively split in half. One side is a bleached, molten desert. It swelters under the heat of an endless high noon, and thick storm clouds that offer shade, but never water. On the other hand is a biting Arctic cold. Here, the stars reign eternally over mile-high glaciers that crush the continents beneath them. In this world of extremes, the only place life may thrive on this planet is in the space between the two extremes, the Goldilocks zone, the thin line between darkness and light, a land where the sun never sets, but never rises either. Despite how different it might seem from the world we know, TRAPPIST-1e may be humanity's best bet for life beyond our sun. One of the missions of the newly launched James Webb Space Telescope is to investigate 1e and its siblings. We know they're as dense as our rocky Earth, but are they as wet, warm, and cloudy as we believe? If so, it's very possible that one day our great-great-great-grandchildren might call this new planet home. And although it might take some adjustments, TRAPPIST-1e might just be more similar to Earth than you think. On the ship to TRAPPIST-1, your mother learns for the first time that she's pregnant. She's worried and scared, but also hopeful and excited for what life on another planet might look like for her and her new newborn, you. Alongside flipping through parenting books, she spends the waking hours of her journey reading about the midnight sun on Earth, how in Arctic regions, the planet's axial tilt makes it so that the sun never sets for months on end, just as it is on TRAPPIST-1e. Only she's surprised to learn how the toll of an endless day can exact upon the human mind, how your body finds it difficult to tell you when to rise and when to rest. She begins to feel it herself, trapped in the cramped, fluorescent quarters of the ship, and she worries for the child she never expected to have. She doesn't know if he'll be able to grow up without ever knowing the tranquility of night. When she finally arrives, the settlement's doctors give her a solution: gene therapy. Your circadian rhythms control 10 to 15% of your genes, they say. By altering those genes, you might stave off insomnia, heart disease, and cancer growth in the same way that polar animals do. Reindeer, for example, deactivate their circadian rhythms throughout the summer sun and reactivate them in the autumn. While some forms of genetic engineering are usually illegal on Earth, in this case, there's a legitimate medical cause, and so you are born a true child of TRAPPIST-1e. At first, it's hard to tell whether the changes took place, given how erratic a baby's sleep cycle can be. But as you age, that cycle never changes. You never have a full 8 hours of sleep, preferring several shorter naps instead. While your mother takes care to give herself the illusion of night by dimming the lamps around dinner time, you're free to stomp around in the light for as long as you can. When she finally tells you it's time for bed, you ask her to leave the curtains open, You don't need them. You never have. And so you bask in TRAPPIST-1E's warm glow, like a cat in a sunbeam. On your very first camping trip, your mother takes you and some friends high into the mountains. There's a few shadows up here, save the ones you cast, and it's easy going. Your mother has walked this path before. But even if you guys happen to get lost, you won't need a compass to find your way home. The sun is your universal reference point, your guiding star, because it's always there, the same place it was yesterday, the same place it'll be tomorrow. Before setting up your pitch black tents, you all huddle around the fire, feeling cold for the first time in a long time. You've never been this close to the dark side of the planet before. In the distance, where the sky turns blue, you make out the faintest hint of light. A single pale dot. You ask your mother what it's called. At school they had you memorize the names of all the TRAPPIST-1 worlds. But not that one. And she sighs. It's a star, like our own red sun, but 1,000,000 miles away. You know this intellectually, but it's hard to care about something so small, so abstract. Seeing your blank face, your mother seizes the opportunity to tell the story over the campfire. This was why she brought you out here, of course. To give you a little piece of the world she once knew. So she starts. When she was your age, your grandfather took her kicking and screaming on a trip much like this one. Reluctantly she went, far from the noise and the glow of the city, into the farm fields of the Midwest. And there she saw what most people on Earth will never see. A clear view of the Milky Way, the galaxy stretched out above her, consuming her. In that brief moment of awe, her imagination stirred with waking dreams of new worlds and new kinds of life. She knew then that she would have to leave Earth. That's why she sacrificed everything she had ever had to come here, to TRAPPIST-1. But you've stopped listening. Instead, you pick up a stick and carve shapes into the ground. You are like most humans who have grown to care less and less about the stars. Right now, more than a third of humanity can no longer see the galaxy above them at night. It got so bad that, in 1994, when an earthquake knocked out power across Los Angeles, dozens of anxious residents called emergency lines to report a giant silvery cloud in the sky. That cloud was the Milky Way. The residents of California had been so blinded by light pollution that many of them had never seen the Milky Way before in their lives. We haven't even traveled to an alien planet yet, and we're already losing connection to the stars, and with them, our most easily accessible source of awe, an emotion clinically proven to stir creativity, generosity, and goodwill. This reality will be even worse when we no longer call Earth home, because despite living on an alien world, the children of TRAPPIST-1E might grow up with a diminished capacity for wonder, a sense of languish that everything is as it ever was and as it ever will be. At school, you practice emergency drills, not lockdowns or even fire drills, but storm drills. In Pacific zones on Earth, typhoons and other tropical storms are so common that they necessitate practice like this. It's the same in the habitable zone of TRAPPIST-1E. You huddle under your desk as the teacher shuts the storm guards and looks at their watch. For a few moments, everyone holds themselves still, silent. You don't live anywhere near the coast, the deep, glacier-fed ocean that stretches around the world, but it doesn't matter. On TRAPPIST-1E, the storms don't come from the ocean, they come from the desert. As the sun boils the dayside air, atmospheric currents carry it up and into the twilight zone, funneling heat towards the cold side of the planet. This minimizes the differences in temperature between the two halves, making TRAPPIST-1E far more temperate than it would be otherwise. This is what allows complex ecosystems to exist. Unfortunately, this is also what precisely causes these desert storms as well. As a result, gale force winds, tornadoes, and hurricanes relentlessly hound the habitable areas of TRAPPIST-1E. Essentially, the same thing that makes life possible on the planet is also life's most constant threat. Later that semester, you're forced to put your practice to the test. The alarm blares and everyone ducks and covers. Yet, you stare out the window. The sun is clear upon the horizon, the same brilliant red. It's a perfectly lovely eternal evening. But as your teacher heads for the shutters, you see it. The aurora. This is a TRAPPIST storm, but of a different kind entirely. Red dwarf stars like TRAPPIST-1s are incredibly volatile, unleashing solar flares greater in frequency and intensity than that of Earth's sun. The stellar radiation emitted can narrow your arteries and even hinder your body's ability to generate new cells. This is why the International Space Station is coated with polyethylene plating to absorb and reflect the solar wind. It is also why, for life to exist on TRAPPIST-1e, both the ozone layer and magnetosphere will need to be exponentially thicker than Earth's. But even if they are, humans still won't be adapted to the worst storms in the way local planets and animals will be. Thankfully, solar plasma moves at less than 1% of light speed. Extremely fast, but not so fast that orbiting satellites wouldn't be able to send out a warning signal, giving scientists, civilians, and schoolchildren a few minutes to respond. As you watch the brilliant green of the aura glimmer above the red sky, you feel awe for the first time, and you wonder how something so beautiful could be so terrible. In high school, you ask your mother for a job in the community gardens. You want to better understand her work in xenobotany, but as a teenager, you can't risk showing a genuine interest in something. So of course you use your requisite volunteer hours as an excuse to spend your free time as her understudy. As she leads you up through the gardens, she says that on Earth most farming took place in the plains, long, flat expanses of land. Unfortunately, that wouldn't work here. A horizontal plane, set against the low angle of the sun, would leave all but the first row of plants in the shadows. So, to build gardens with plants the sun could reach from its limited angle, the first TRAPPIST farmers had to look at the mythical hanging gardens of Babylon and the many-tiered rice farms of East Asia for inspiration. Water is funneled up through aqueducts, and then spills over the terraces to keep the plants hydrated. At the highest tier of the gardens, monumental tomato plants tower over you, nearly 6 meters or 20 feet tall. While TRAPPIST only emits a fraction of our sun's light, the growth is never halted by night or destroyed altogether by the cold of winter. Even smaller plants can grow indefinitely, like trees, branching to incredible heights. Your job is to trim and water them TRAPPIST style so that they grow thicker at the bottom rather than outward in thin tendrils. It's tedious work, but rewarding. While your mother helps you sometimes, she finds the perennial nature of TRAPPIST-1 farming a little too easy. On Earth, she says plants are more vulnerable. There's a challenge in producing a whole year's worth of food in the span of just a few months. But here, even a blight doesn't spell disaster. You can just plant more tomorrow. And besides, you know she's needed in the far more important task of cataloging the native flora of TRAPPIST-1e, which evolved to be entirely black so as to attract as much light as possible. If she can adapt their alien chemistry for human use, the potential benefits are immeasurable. An entirely new biosphere's worth of potential cures that could help not just people on TRAPPIST-1e, but all of humanity. You wish you could join her in that work, but trimming tomatoes is okay for now. In your last year of high school, you receive a full-ride scholarship to study botany at university. However, the university is on Earth. Your mom is excited that you'll be going to her planet, her home. But for you, the shock of leaving your home and living on your own for the first time is compounded by the shock of moving not just out of state, or even to a foreign country, but to a foreign world, entirely alien to you. Once you land on Earth, you feel existential dread looking up at the night sky, realizing for the first time the vastness of the universe thanks to the bright look of the Milky Way on one of Earth's nights. Such a weird concept to you, still. You wear thick sunglasses and sunscreen to protect yourself from the light of a bright yellow star, which you find blinding compared to the dim light of your red sun. You often get lost, disoriented, and disquieted at a sky which is constantly changing. The sun, stars, and moon no longer serve as a stable reference point, limiting your sense of direction. You lie awake at night, jet-lagged, marveling at the uncanny silence. The white noise of storms and wind, which once comforted you, are gone. Thankfully, the other students come from faraway worlds as well. Water worlds, verdant moons, places far stranger than your temperate home. And so, all of you, humans from across the galaxy, adapt to the strangeness of Earth together. Your mom tells you you're human, but here on Earth, you feel very much alien. In the year 1609, Galileo pointed one of the first telescopes ever created up at the heavens, and what he observed sparked a revolution of curiosity that has been central to every single human generation since. Galileo saw mountains and craters on the surface of the moon, the arm of our Milky Way galaxy arching across the sky, and an endless universe riddled with countless stars. The mysteries of outer space were boundless, and the journey towards discovering them had only just begun. Over 400 years later, and our obsession with the enigma that is space has only managed to intensify, fueling many great technological advancements that have made our ever-expanding universe seem smaller and its boundaries closer than ever. On the 25th of December 2021, NASA launched humanity's most powerful telescope yet. More than 30 years in the making, $10 billion spent, a successful launch, 50 intricate outer space deployments, and a distance of over 1.5 million kilometers traveled from Earth, the James Webb Space Telescope has finally delivered its first full-size images of our universe, marking an era of space discovery that promises unique and unprecedented views from across our own solar system to the very heart of the universe. The James Webb Space Telescope, JWST for short, has been designed to look more than 13.5 billion years into the past to study the farthest and oldest regions of space, peering back into the early days of the universe. Its aim is to look at the first galaxies that started forming and emitting light right after the Big Bang. It's no wonder that scientists often refer to telescopes as time machines. In them lies the power to see what our universe once was, and perhaps answer one of humanity's most perplexing existential questions. How did we get here? And right now, Webb is our best chance at finding an answer to that question. However, to fully understand what makes Webb so special, we have to travel back in time to the year 1990, when the Hubble Space Telescope was launched. The Hubble Space Telescope embarked on a mission similar to Webb's. Its purpose, just like Webb's, was to study the universe like it's never been studied before, and to bring us closer to understanding our existence and our place among the stars. Over the past 30 years, Hubble has brought us images of galaxies we never knew existed, star clusters, and nebulae like we've never seen before. These images helped illustrate how in the early days of our universe, just millions of years after the Big Bang, cold clouds of gas and dust evolved into swirling, coalescing galaxies teeming with stars. Sadly, that was just how far Hubble could see. In order to observe how these first galaxies were born, we needed a bigger telescope, one that wasn't just more powerful, but that could also operate in the infrared. So just a few years after Hubble was launched into space, scientists began working on the next big telescope. Today, Webb is 100 times more powerful than Hubble, and its ability to observe infrared light opens up a new universe of possibilities. Literally. Ever since Edwin Hubble discovered that the universe is expanding, we've known that galaxies have been receding at faster and faster speeds. Light from these galaxies is stretched to longer wavelengths as it travels through space, which is why they're only visible through infrared. Hubble, the telescope, is only able to see light on the visible spectrum, which means it's limited in the amount of information it can fetch us about these earliest galaxies. But with Webb, we finally have the ability to observe them. To detect these infrared waves, Webb traveled more than 1.5 million kilometers away from Earth's warm atmosphere, to a very cold region in space that is protected from our planet's infrared radiation. Built into this telescope are huge sun shields as big as the tennis court that protect it from the rays of the sun and help keep its temperature at minus 233 degrees Celsius, so it can be cool enough to detect infrared radiation from the early days of the universe. This is the first time in history of our species that we've been able to look at our universe with such depth and detail. And the first images NASA released on July 12th are proof that we've entered a new space frontier that is bound to bring us closer to understanding our place in this ever-expanding universe. Let's begin our journey back in time with the closest image Webb has taken. This is called the Southern Ring Nebula. It's a planetary nebula in our own Milky Way galaxy, 2,000 light-years away. Despite its name, a planetary nebula doesn't have any planets. The name is simply inspired by its round structure. A nebula is clouds of dust that are thrown out by the explosion of a dying star. You can see enormous clouds of gas thrown out by this red giant in the center of the image. This image utilizes Webb's near-infrared camera, or NIR cam, which looks at the shortest infrared wavelengths. When we switch to its MIRI, or mid-infrared instrument that can observe longer wavelengths, you can actually see that it gives us an unprecedented look into the heart of this nebula. Right here, you can actually see two stars at the center of the system, with the dimmer one being a white dwarf at the tail end of its life, and the brighter one, a red giant, at an earlier stage of its dying process. The pair of stars are locked in each other's orbit in a cosmic embrace, which leads the dimmer star to spray ejected material like a sprinkler, resulting in these jagged rings. Stars are critical to life as we know it. With Webb's powerful mirrors and its ability to peer behind the thickness of gas and dust, we'll be able to study the death of stars like we've never done before. This could give us a greater understanding of the chemicals and the elements that are discharged from stars as they evolve through time, and whether these components are the building blocks that are needed to spawn life as we know it back on Earth. But the birth of stars is just as important as their death. This image of the cosmic cliffs in the Canary Nebula, 7,500 light-years away, offers a breathtaking view of the clouds of gas and dust actively coming together to form new stars. This is one of the most active star-forming regions in our galaxy, a star nursery that could give us tremendous information on this creation process. When we switch to the MIRI once again, you can see the infant stars behind this ethereal cloud of dust. Being able to see what is behind their cosmic clouds is incredibly important when we look at galaxies as a whole. It can enable us to estimate the total mass of stars in a galaxy with more accuracy. Speaking of galaxies, 300 million light-years away lies the tightest galaxy grouping we've ever discovered. These 5 galaxies are called Stephan's Quintet, and they are all bound to crash into each other and eventually merge. Actually, 2 of them are already in the process of doing exactly that. This image of Stephan's Quintet is the largest of Webb's initial images. It might not look like it at first glance, but what you're seeing here is actually a composite of over 1,000 images made up of over 150 million pixels when combined together. Zooming in on any part of this picture will show you hundreds, if not thousands, of galaxies waiting to be discovered. What's even more fascinating is that when we switch to the mid-infrared instrument, we can spot never-before-seen details of Stephan's Quintet. That very bright structure in the uppermost galaxy is actually a supermassive black hole, 24 million times the size of the Sun, and actively increasing in density while emitting more energy than 40 billion suns put together. Just pause and think about that for a moment. These new images provide us with valuable insights into galactic interactions that may have driven galaxy evolution in the early universe. The early universe, Webb's primary mission. This is what is called a deep field image. Deep field is a long-lasting observation into a particular region of space, intended to collect light from the faintest, furthest objects. Peering 4.6 billion years into the past, this image shows the galaxy cluster SMACS 0723 at its center, alongside shimmering stars, warped light trails, and thousands of extremely distant jewel-like galaxies. It's the deepest and sharpest infrared image of the early universe we've had so far. But despite its magnificence, what's most interesting about this deep field is the warped light trails around the galaxy cluster's edges. This galaxy cluster is so massive that it warps space-time, and ultimately the light of stars and galaxies located billions of light-years behind it. This is called gravitational lensing, and acts like a cosmic magnifying glass, bringing the light of galaxies almost 13 light-years away, potentially making them some of the oldest galaxies we've ever observed. Without a doubt, these early images are breathtaking and already showcase the huge capabilities of Webb. But taking pretty pictures isn't the telescope's only superpower. It can also study the atmosphere of planets. For a while now, we've been searching for exoplanets, which are planets outside our solar system, orbiting around a star similar to our Sun. We've discovered about 5,000 of them so far, with our main goal being able to find one that's hospitable to life, and ultimately finding some of that life. When analyzing the atmospheres of exoplanets, we look for elements such as methane, oxygen, or nitrogen, ingredients present in our own atmosphere that could signify the presence of life on these planets. So far, the universe hasn't offered us any signs of life. However, this graph captured by Webb of the hot gas giant exoplanet WASP 96b could be our first step towards locating some extraterrestrials. The observation reveals the presence of a very specific gas molecule, water vapor. While Hubble analyzed numerous exoplanets' atmosphere over the decades and detected water in 2013, Webb offers a more detailed observation, and a giant leap forward in tracking down habitable planets beyond Earth. This image is only a glimpse of Webb's massive ability to capture precise atmospheric elements hundreds of light years away. We've always wondered whether life exists beyond Earth, and Webb could be the tool to help us answer this question and change the meaning of our existence forever. The James Webb Space Telescope has only begun its journey, and the road ahead is still long and daunting. analyzing the universe's origins, understanding the birth and death of stars, discovering distant galaxies, and finding exoplanets are only just the beginning. The truth is, looking more than 13 billion years into the past is bound to raise more questions than we could ever imagine, but it also has the potential to answer questions as well, some of which we've been asking since the days of Galileo, and even new ones we never knew we had. When Galileo raised his telescope to the sky and looked at the craters on the moon, he acted on an almost instinctual human curiosity that has been with us ever since the dawn of time. More than 400 years later, this same curiosity is bringing us even closer to our cosmic background. Earth is only a small stage in the cosmic arena, and with the beginning of a new era in space discovery, we now know that more than we ever did before. There is no doubt that in the upcoming years, Webb will bring the universe even closer to us and help us know more about the reality of our cosmic existence. So whenever you find yourself looking up at the night sky and its beautiful stars, remember, somewhere, something incredible is waiting to be known. On the 15th of August, 1977, Ohio State University's radio telescope, Big Ear, was listening to the apparent emptiness of the cosmos, as it did every other day. The Great Silence, as it is often called, persisted, disturbed only by the noisy residents of Earth or the galactic star shows of solar births and ultimately their inevitable explosive deaths. That day, however, their telescope would receive a rather strange signal as it pointed towards the constellation Sagittarius. It wasn't similar to any signal they had received in the past. The signal only lasted for 72 seconds, and it has never been detected since. Many attempts have been made to explain the origins of the signal, including suggesting that it was man-made. Its non-random nature strongly suggested that the signal could be of artificial origin, which led people to believe that the signal might be from another intelligent civilization. Although we don't have any further evidence about the signal, despite numerous attempts to redetect it, the WOW signal remains unexplained to this day. It is the closest humanity has ever come to communicating with another potentially intelligent life form. And for all we know, that could have been our only chance. Which really makes you wonder, if we came in contact with an extraterrestrial life form, how would we communicate with them? And the better question is, should we even try? Let's start by answering the last question first. Should we even try to contact an extraterrestrial and possibly intelligent life form? Historically speaking, at least, the relationships between discoverers and the discovered haven't gone very well. Those that embark on the risk of exploration are often technologically superior, and the natives they discover stand no chance of being able to defend themselves. An intelligent life form that is able to make the interstellar journey to Earth from a distant galaxy is orders of magnitude more advanced than we are as a species. Given that superiority, we would be essentially at their mercy. Whether they choose to be hostile or friendly is completely up to them. This was the exact worry of Stephen Hawking, but these warnings are possibly too little, too late. You see, with televisions and satellite communications, we've been sending out our signals for over 70 years at this point. Knowingly or not, we've been buzzing our planetary sirens for a long time. We've been loud and clear about where we are, and so it's not necessarily going to make much of a difference if some other civilization is actually listening. Perhaps a better course of action would be to try and make sure that the signals we do end up sending are the right ones that convey our non-hostility and accurately represent who we are. Besides, it could be argued that a civilization that is so advanced that it can reach other stars is simply beyond the idea of aggression that we tend to show. Our aggression evolved as a trait because it helped us find and protect resources when they're limited, and while an extraterrestrial civilization should have the same problems during its infancy, by the time it can make a journey to a different star, it's likely to have figured out practically an infinite source of energy. It's pretty unlikely that a civilization that is struggling to make ends meet will have resources to travel light years to another planet. But how should we send our messages? Well, the WOW signal from earlier is a good place to start. The wavelength of this radio signal, roughly 21 centimeters, has been used to map the universe. It's used as such because hydrogen gas is by far the most abundant element in the universe. This 21 centimeter wavelength is known as the hydrogen line. It is everywhere in the universe, and so the electromagnetic radiation it emits when its energy state changes is something very useful to astronomers. The hope is that technologically advanced civilizations will see a similar significance for 21 centimeter signals and recognize them when they're sent. 21 centimeters is also used as a unit of measurement in plaques and other interstellar messages that are hurtling through space as we speak. But more on that at a later time. Once the mode of the message has been figured out, we have to decide what that message will contain. Here, we need to remind ourselves, once again, that the civilization we're trying to talk to could be a far superior one than our own. That would give us a greater freedom in what we want to say in the message, since they should be able to crack the code, if you will. You see, some of the messages that have already been sent, including the famous Arecibo message, or the plaque that the Voyager crafts are currently carrying, are very complicated. These messages are subjective, they can be interpreted in many ways. You could have people from all around the world each come to different conclusions. So if even humans can agree upon what's being said, the very species that made the message, then how can we expect another species to understand it? Additionally, what is it to say that the extraterrestrial civilization shares our visual senses, or any of our senses for that matter? What is it to say that the images of smiling people in the plaques of Voyager 1 and 2 are not hostile signs of aggression in another planet, in another time? Our tendency to be so centered around the human experience can really get in the way. To eliminate these problems, our messages should be objectively universal and should make no Earth-centric assumptions about the experiences of our galactic neighbors, at least to start. Crafting a message for an alien species is a good exercise for humanity to truly understand who we are. So far, only math and maybe some branches of science seem to be truly universal, meaning their contents seem to be true everywhere we look. The Pythagorean theorem holds as well on Earth as it does anywhere else in the universe, as far as we know. Things like this are our best bet to initiate communication with a civilization we share nothing else in common with. The message should also be as non-random as possible, which sounds weird. It should be repetitive so that the chances of detection is increased, and it should also be as time independent as possible. Space is massive. Interstellar distances means it could take thousands of years for them to reply, a timeline in which the Earth and us humans may change drastically. Even light speed is pretty slow in the grand scheme of things. These and other such details need to be part of a protocol that can be used when sending messages to other stars and beyond. We also need to figure out who and what gets to represent us all in humanity's most important text message. At the moment, these protocols have no recognition in national or international law. But what if they show up right on our doorstep? What if they were already listening in on our very first television broadcasts and radio signals and have been en route ever since? Is there a post-detection protocol? Who does what? And who gets to decide? Theoretically, such a post-detection protocol would fall under the review of SETI, or the search for extraterrestrial intelligence, and they do have one. The movie Arrival portrays this very scenario. 12 UFOs land in 12 different parts of the world, and governments are left scrambling to make sense of it all and respond. In such a scenario, the front line would be composed of not soldiers and tanks, but rather cryptologists trying to decode or decipher whatever messages are being exchanged, as the movie depicts. Xenolinguistics, or alien language, would be the focal point in the days after first contact. Deciphering an alien language would be especially hard, if not impossible, since they might not have the natural sense of grammar and structure that our languages do. Another facet of first contact would be the risk of a viral infection, both to us and to them, whoever they may be. Of course, they would need to be biochemically similar to us for a transmission to occur and cause harm. But as long as there is a possibility, a first contact would most likely initiate a lockdown of the region in which it took place. If we can't even be immune to the viruses on Earth, the planet we evolved to live on, we shouldn't try our luck with viruses from another planet. The political impacts of first contact would be immense. It would usher in a new era for humanity, and to be able to claim such an achievement would be the first thing on every country's political agenda. This could make the first contact a destabilizing force in the world. Religions will be questioned, and so will science. The presence of just one extraterrestrial species will significantly change the probability of others being out there too, and alter our understanding of life forever. We will remember history differently, time before and after first contact. The lack of an internationally ratified protocol with the force of law behind it means every country is left on its own on how to react. That's bad. The apparent reward for an individual country or person to be the first is far greater than the reward for a level-headed approach, even though it could likely end in the extinction of the human race. We need a post-detection protocol, but it's not that easy. Countries that worked together in the past may not work together now. Russia and the United States have worked rather seamlessly, or so it would seem, in their space missions, especially during the long periods in which America couldn't fly to the International Space Station. On the other hand, if you look at global efforts aimed at denuclearization, it's a different story. So, if an international protocol is so important, why doesn't one exist? Well, it has to do with how real the problem seems. It just doesn't seem very likely that we will encounter another life form. Earth's to-do list is quite full at the moment. But I just don't understand how countries that are willing to invest hundreds of millions of dollars to create the next big telescope can be so oblivious to the possibility of actually finding something. These technological efforts seem less focused at uncovering the truths of the universe and more at winning the next race for global supremacy. There's other scenarios to consider too. For example, what if the other species is less intelligent than us? Well, in that slightly less interesting case, we'll likely be the ones to make the discovery, and we'll get to call the shots. What if they are exactly as intelligent as us humans? Probabilistically speaking, this is the most specific of all the scenarios and is therefore the least likely. Then again, by the time we communicate with each other and receive replies, one or even both species might be extinct. Another creepy possibility is that of past visitations. What if we have been visited before? And what if we've been being observed ever since? The silence at the heart of the Fermi paradox may reflect stealth, not absence. These are all possibilities that we have to consider in our search for extraterrestrials. As exceedingly rare as it may seem, the quest for other life forms, the desire to answer the question, are we alone, is incredibly strong. So strong, in fact, that humanity seems to keep looking for it, even if it leads to its own demise. So, how long before all this becomes a reality? How long before interplanetary travel is an everyday affair? Well, as you can imagine, that's a complicated question. It is rocket science, after all. On May 30th, 2020, SpaceX launched its first crewed mission to the International Space Station. It was the first crewed mission with American crew, from American soil, in an American spacecraft in a very, very long time. And while the contents of the mission weren't anything new, carrying cargo and crew to the ISS, what made this launch so special was that it was the first commercial flight to have done so. And all this took place in one of the most trying times humanity has faced in recent history. With protests all across America and a health crisis that has crippled the entire world like never before seen, the launch still went through. And that means something. And the launch, well, it didn't just go on. It was the most widely watched online NASA event in history. And while its total viewership still pales in comparison to that of the Apollo 11 launch, where nearly 1/6 of the entire world tuned in, something tells me that we're about to break that record sooner rather than later. As I just mentioned, SpaceX was the first to commercially do all of this. But what does this mean, and why is that important? Well, it means that NASA is essentially outsourcing the job of innovating and building the rocket to other companies like SpaceX, Blue Origin, Boeing, and so on. They all bid for an opportunity to build, and NASA pays whoever has the best ideas through a contract. In doing so, NASA is taking a lot of the weight off of its underfunded shoulders and is using the powers of the free market to its benefit. Companies competing to see who can innovate better, who can create rockets that are faster, more efficient, and cheaper. It's a very important first step to create and maintain a significant presence in low Earth orbit, and that's where the logistics of space travel change significantly. Low Earth orbit. A popular saying goes that getting to Earth's orbit is halfway to anywhere in the universe. You see, gravity can sometimes be benign. After all, we spend our lives getting used to its effects and sometimes just forget it's there. But when you're dealing with potentially millions of pounds of stuff that needs to be propelled upwards, we have a problem. As soon as we escape gravity, however, things change drastically. There is quite literally nothing to drag you down, or up, or anywhere for that matter. Just the slightest of pushes can propel you endlessly through the vastness of space. To give you a sense of the impact gravity has on space travel, during the Apollo 11 mission, reaching Earth's orbit took nearly 27 times the propellant compared to the rest of the journey, including re-entry into Earth. Earth's gravity is an endearing force, and in this case, a costly one. The simplest way to get around this problem is to have an outpost in low Earth orbit or somewhere else, an interplanetary pit stop, if you will, where scientists will work and stock up on supplies and refuel before they embark on their deep space adventures. The International Space Station, humanity's most prominent low Earth orbit presence at the moment, may help us stock up on food and similar supplies, but when it comes to fuel, things get complicated. We'll have to look a bit further, 380,000 kilometers to be exact. It's a journey we've already made. You see, the moon potentially has everything we need to make propellant, oxygen and hydrogen. And I say potentially because scientists are still not sure about the availability and accessibility of water on the moon. But they do know that lunar dust contains oxygen, which accounts for most of the weight of the propellant anyway. All this means that the moon could become the perfect fuel depot for humans before they head out to further planets such as Mars, given launches from the moon only have to fight 1/6 of the Earth's gravity. This crucial step has seen promising progress in the last few years, with numerous companies already looking into technologies that can help astronauts mine the lunar surface. Also on the cards is a lunar space station, intended to get scientists more used to deeper space travel before they head off to further planets. Known as the Lunar Gateway, this project is part of NASA's Artemis program. The missions are said to have a man and woman back on the surface of the moon by 2024. Understandably, it's an optimistic deadline. NASA is used to that. Who knows, maybe with the push of commercialization, we may get there sooner than we think. Fuel has also seen a few breakthroughs in recent decades, the most notable of which is ion propulsion. Instead of using chemical propellants, these systems propel ions, charged particles, using electromagnets. Add to that the lack of drag in space, and all you need is Newton's third law to push you into the vastness. There's a catch though. This ion propulsion, while significantly more efficient than the traditional propulsion, provides only minute levels of thrust. The force it'll be pushing the spacecraft with is equivalent to the force a piece of paper exerts on your hand. It's an extremely small force, but keep that up for days, weeks, or months, and it adds up. So much that it can possibly reach speeds of up to 200,000 miles per hour, nearly 6 times of what is traditionally possible. But the gentleness of the force means ion propulsion is not suited for reaching low Earth orbits against the forces of gravity. Rather, it's only useful in zero or microgravity situations. I personally think future propulsion systems will be a hybrid of both, liquid propulsion and ion propulsion. But what about time? You see, the Earth is about 200 times further from Mars than it is from the moon. That's 2 orders of magnitude. Using currently existing technology, and even with some significant advances such as ion propulsion, a journey like this will take a few months at least. It's really hard to internalize just how large the distances we're dealing with are. For example, in the time that you've watched this video so far, Voyager 1, the furthest man-made object, has traveled over 4,000 miles. It's currently traveling at an incredible speed of nearly 38,000 miles per hour. But even at that speed, it took nearly 35 years to travel through the solar system. The resupply outpost could potentially solve some of the problems, allowing missions to carry larger payloads than before. But even then, the duration can have mental implications. Long periods of isolation, as all of us have probably experienced by now, can lead to a loss of motivation and affect our ability to work, which is a problem when you spend millions of dollars training astronauts. Couple that with the idea that food is running out and homesickness unlike any man has ever experienced before, and you have mental walls crushing you from both sides. One way to solve this issue might be to not have the astronauts be awake for most of the flight in the first place. Yes, the key to solving this problem might be hibernation. This field has seen increased attention in the past few years, mainly due to spaceflight. You see, most of the food we eat is used up just to maintain our body temperature. By lowering this temperature, we can potentially cut down on caloric intake by 50%, if not more, essentially doubling the food supplies. It could also be a way to prevent muscle atrophy in space that astronauts have always suffered from. For longer flights, such as those being planned to Mars, this becomes an even bigger issue, and hibernation may be the only way to counteract it. Hibernation research is still in its infancy, and the most remarkable results are still in animals like squirrels and bears. But scientists believe there aren't any biological bottlenecks as to why we shouldn't be able to accomplish hibernation in the future. The state of hibernation we're interested in is currently prevented by our bodies through shivering. If we're able to safely turn that reaction off, scientists believe hibernation could be used in short chunks to prolong supplies and preserve the mental well-being of the crew in man's greatest adventures. We're still in the dark about a lot of the effects that long-term space travel has on the human body, and missions such as Artemis can help answer them. But we can go a step further. Neuralink could be another part of the space puzzle, albeit one of the less obvious ones. In its primary stages, Neuralink intends to help patients with diseases like Alzheimer's or Parkinson's, but the goal is also to augment us humans using the power of AI. Within a few decades, and some exponential growth, we could have the ability to upload our consciousness to a computer. We could then essentially explore other planets with the dynamic intelligence of a human being, but without the physical presence of one. Of course, spaceflight with AI may not be manned in the traditional sense, but it gives the opportunity to test the waters. There's other reasons why artificial intelligence is important in the next generation of manned spaceflight as well. There are 2 factors that are very new to modern spaceflight. Commercialization, which we've already talked about, is one of them. But the other one is AI. We've never had it before. Apollo 11 famously had a guidance computer with capabilities that would pale even against the oldest iPhone. To have the power of AI in such situations could radically change what we're able to achieve in the future. In addition, beyond a distance of about 300,000 kilometers, even at light speed, information is going to take more than a second to reach, and for larger distances, this is only going to increase. Given that flight functions, such as fuel burning, have to be precisely timed and flawlessly executed to reach destinations in deeper space, even a momentary lag can be catastrophic. The presence of AI can really help astronauts when there is no Houston to call on. AI can also play a crucial role in asteroid mining as well, but unlike the planets or the moon, we know very little about specific asteroids. Landing on their uneven surfaces becomes a task no astronaut has any prior experience in. AI can help learn the landing surface in real time and allow for a safe landing. But it's one thing to do things safely, it's another to convince the public about it. You are, after all, much more likely to die by choking on your own food while eating rather than in a plane. But I'll let you guess which activity makes people more anxious. That skewed, incorrect perception of how unsafe something is could be our greatest defense mechanism. It might as well be the fear of consequence that has made planes the safest mode of transportation. It's also this fear that has allowed nuclear power generation to lead to fewer casualties than solar power. Spaceflight will likely follow a similar path to safety. But then again, how safe does it need to be? After all, if the extinction of the human race is what should drive our space endeavors, it only needs to be safer than the likelihood of extinction, right? Spaceflight fatalities currently have a likelihood of around 3%, and in 2018, the likelihood of total human obliteration was 1%, which is kind of an incredibly high number. If the number doesn't go down orders of magnitude, is spaceflight going to become a safer risk than the alternative of complete destruction? Public perception plays a crucial role in this aspect of spaceflight. At the end of the day, that is what determines how well funded the efforts and how quickly and safely these goals are achieved. Accidents slow down the progress of spaceflight remarkably and destroy public support. But the fact that the recent launches took place against a backdrop of global anxiety perhaps goes to show that spaceflight still retains excitement to unite us all. It has a unique ability to captivate anyone and everyone by satisfying the carnal desires of flight and exploration. Even if it isn't us inside the cockpit, it's quite literally an escape from our worldly problems. During the course of my research for this video, I was just surprised how sporadic the progress of spaceflight has been. Just based on the content of certain articles and their predictions, it's really quite hard to tell whether they were written 10 days ago in response to the SpaceX hype or 10 years ago. However, if you read an article about wireless charging or bezel-less displays, you can immediately tell which generation of cell phones the article is talking about. Such indistinguishable progress just goes to show how stagnated space exploration has been lately and how the public hasn't really cared enough to stay in the loop. The Saturn V, the rocket that took man to the moon, is, at the time of writing, still the most powerful operational rocket in the world, and it's been almost 50 years since its final flight. You could look at this in two ways. 1. Progress in spaceflight has been disappointingly slow. Or 2. The Saturn V was so good and ahead of its time that nothing else has come close since. I think it's a little bit of both, and I know I always do this. The fact that the Saturn V still sits on that throne is a testament of what humanity can achieve when it's truly inspired. And while that lack of achievement in recent times can be really demoralizing, it also makes for a future worth looking forward to, one to be excited about. And I think that's what Elon Musk has in mind when he talks about colonizing Mars. The reality is, we know very little about Mars, and at the end of the day, it may not be able to sustain life after all. But the drive to get there, the pursuit of such lofty goals, its technological indulgence of the highest order, and the prospect of seeing another rocket tearing through the sky, well, it has the ability to inspire generations once again, to give us a reason to be excited. Excited about tomorrow, excited about the future, or excited to simply be alive. But even if we end up doing none of this, even if we achieve none of the things we set out to achieve, even if we fail launch after launch and make error after error, of course I still love you.
It's common to hear that space is the final frontier, to go where no man has gone before. But in actuality, it's the beginning of the future. The knowledge we gain about the universe increases day by day, but our means of accessing it is a slow and sometimes even painful journey. Since the 1970s, the American spaceflight industry has been moving in the wrong direction. From being able to send humans to the moon atop a Saturn V rocket, to then only being able to send astronauts to the ISS aboard the space shuttle, to now having nothing at all. Space has been a place only explored by the biggest governments on the planet. But now, the tides are shifting. If the most powerful countries on Earth aren't willing to put effort where it's due, others have to step up. The engineering feats from the 20th century have put us in a position to accomplish all of our goals, but yet, the entire reason we began has been forgotten. The reasons these rockets were built, the places we've went, the things we've achieved, it's all just been swept under the rug. Until now. The private spaceflight industry is growing at an unprecedented rate. The biggest problems with space travel are being tackled by some of the smartest and richest people on this planet. And it's not a coincidence. Space travel is one of, if not the most important issues today. It's not a cultural issue, it's not a political issue. It's a matter of evolution. We've always been explorers, moving from sea to land, to moving across entire continents, traversing oceans, covering every single inch of our planet. And now, it's time to go even further. As of 2019, only 4 entities have put a space capsule in orbit and successfully returned it back to Earth. The United States, Russia, China, and SpaceX. That's it. Elon Musk took a sum of $100 million and, in 2002, Space Exploration Technologies, or better known as SpaceX, was born. They're in a league of their own, launching some of the most powerful spacecraft since the Apollo era. SpaceX is competing with some of the most powerful forces in the entire world. Their goal is simple: to enable humans to live on other planets. And as of right now, the destination is looking like Mars. SpaceX has revolutionized the commercial spaceflight industry, and are the ones reigniting the public's interest in space travel. But the company hasn't always had the reputation it does now. The Falcon 1 rocket was SpaceX's first, and almost last venture in commercial spaceflight, but it's perhaps the most important one of them all. From 2006 to 2009, Falcon 1 attempted 5 flights, but it wasn't off to the best start.
When you had that third failure in a row, did you think, I need to pack this in?
Never.
Why not?
I don't ever give up. I mean, I'd have to be dead or completely incapacitated.
But on September 28, 2008, things went a little differently. Falcon 1 carried a 165 kilogram simulated payload into orbit, successfully. For the first time, a privately built liquid-fueled booster reached orbit. The Falcon 1 rocket is the first in the family of Falcon rockets developed solely by SpaceX. It stands 21 meters high and was capable of carrying over 500 kilograms of payload to low Earth orbit. For its time, this was the most important event in spaceflight history. 500 kilograms isn't much, but this was the start of everything. It created the roadmap necessary towards a future of cheaper and more reliable space travel. That day, that first successful flight, was what single-handedly saved SpaceX from extinction. After the first 3 failed attempts, SpaceX was on life support. The $100 million that was put into SpaceX was all gone. If this 4th flight hadn't succeeded, SpaceX most likely would have gone under, and all the things you're seeing them do today would have never happened.
I messed up the first 3 launches. The first 3 launches failed. Unfortunately, the 4th launch, which was that was the last money that we had for Falcon 1, the 4th launch worked, or that would have been it for SpaceX.
Simply putting something in orbit is one of the hardest tasks there is, and all these failures show how challenging the process really is. But they had done it, and it saved everything. On December 23rd, 2008, NASA awarded commercial contracts out to private spaceflight companies, 19 of which went to a company called Orbital Sciences, while 12 went to SpaceX. The contract was valued at over $1.6 billion. From this, SpaceX was saved, and they boomed, in a good way this time. In 2010, SpaceX developed Dragon, and, yet again, made the world's first commercially built spacecraft to be launched and recovered successfully from orbit. The Dragon spacecraft is the future of manned space travel. It can deliver not only cargo, but is also capable of carrying up to 7 passengers to Earth orbit and even beyond. Also, in 2010, a new addition to the Falcon family would be introduced. The Falcon 9 was made with reusability in mind. It's a 2-stage rocket with 9 Merlin engines, that's over 3 times the size of the Falcon 1. Both of these, the Falcon 9 rocket and the Dragon capsule, were launched together for the first time in December 2010. A year and a half later, they were sending Dragon to the International Space Station, becoming, yet again, the first private spacecraft to dock at the ISS. Since then, they've been doing routine resupply missions to the ISS funded by NASA. So far, they've done over 18 resupply missions with only 1 failure, and they have no plans of stopping. With all the success of the Dragon spacecraft, let's not forget about the Falcon 9 itself. After years of work, in 2014, the first test flight of the Falcon 9 reusable took place. The rocket is the same as any other Falcon 9, but now, the rocket was capable of lifting off of the ground, launching into the sky over 250 meters, and, after hovering, returned back to the launch pad, in one piece. After more testing, they decided to try and test these for real. But, just as the Falcon 1, it didn't get that great of a start. But, you can only mess something up so many times before it starts to go your way.
5, 4, 3, 2, 1, 0. Liftoff of Falcon 9.
For the first time, we had reusable rockets, and spaceflight was changed forever. SpaceX, on a 2-stage Falcon 9 rocket, had successfully launched 11 satellites into orbit around the Earth, and returned their first stage back to Launchpad 40 at Cape Canaveral, Florida. Just 4 months later, in April 2016, they made history yet again. Falcon 9 launched Dragon on a cargo resupply mission to the ISS for NASA, and for the first time, landed the first stage of the Falcon 9 back on Earth, on a drone ship in the middle of the Atlantic Ocean. SpaceX had proved that they could not only land a rocket back on land, but also with extreme precision on a barge in the middle of the ocean that's less than 100 square kilometers in size. These launches are quite literally changing the world, each and every time. But let's get bigger. The Falcon Heavy is an engineering masterpiece. Tens of thousands of hours of work, years of innovation, all with one goal in mind: carrying humans into space, returning them to the moon, and even beyond. The liftoff thrust of the Falcon Heavy is the same as 18 Boeing 747 aircrafts going at full power, all at once. To even try and compare the two is embarrassing. The first stage of the rocket is composed of 3 different Falcon 9 cores, with a total of 27 Merlin engines all firing simultaneously. It's essentially like you're launching 3 different rockets at once and making sure that they all work together. Shortly after liftoff, the center core slows down to conserve fuel, while the 2 side cores use almost all their fuel, saving only a portion of it. Once the fuel is exhausted, about halfway through the flight, the side boosters separate and return back to the launch pad for a simultaneous landing. As for the center core, it's used to push the payload into orbit. It'll be going too fast to return back to Cape Canaveral, so once it's completed its mission, it too will return to Earth, but not on land. It'll land on a barge approximately 1,300 kilometers off the coast of Florida. 1 rocket, 1 launch, 3 different landings. The space shuttle that NASA used from 1972 to 2011 cost approximately $60,000 for each kilogram of material to be sent into orbit. The Falcon Heavy can do the same thing, but for just 1,300. Nothing else even comes close, actually. With the ability to lift over 64,000 kilograms, a mass greater than a 737 jet with passengers, luggage, crew, and fuel, the Falcon Heavy can lift over double what the next closest competitor can do, at a third of the cost. If there's any rocket that's currently being manufactured in the modern age that is capable of sending humans into deep space, it's the Falcon Heavy. It's the most powerful rocket in the world currently in use, and the fact that you can save and reuse over half of it makes it the most efficient rocket ever made. Reusable rockets are a necessity. Why? In order to live on other planets, the only way that will be feasible for the masses is to reduce the cost of spaceflight drastically. Right now, the Falcon Heavy costs about $90 million per launch. If we can engineer these rockets to have a lifespan of 100 launches, and we're looking at under $1 million per launch. Compare this to the Saturn V in 1969, which in today's money cost a few $billion per launch, and you'll start to see the power of reusability. Just the first stage of the rocket accounts for over 75% of the total cost. The fuel used on a Falcon 9 launch is cheap when compared to the price tag of the rocket, coming in at only around $250,000 per launch, or about 0.3% of the total cost. A Boeing 737 costs around $100 million on average. Compared to the Falcon Heavy at around $90 million, it's essentially the same. Now imagine that every time we take a flight around the world on one of these planes, we destroyed it afterwards. Imagine that every time we drove to work or school, we had to destroy the car. But yet, when it comes to spaceflight, rockets tend to fly once and only once, despite the rocket itself being the majority of the cost. This doesn't make much sense. Looking back on history, reusability is the common denominator when it comes to widespread access to anything. If cars couldn't be refilled and taken on multiple trips, nobody would own them. If airplanes were all simply one-way flights and couldn't be reused, no one would be flying. Imagine having a rocket with humans that could be launched, sent to orbit, returned to the surface, refueled, and then launched again, multiple times, in the same day. This is the key to affordable space travel. All we have to do is perfect it. Once perfected, an even bigger rocket in development by SpaceX will revolutionize the way we travel. The BFR, or Big Falcon rocket, will be over 118 meters high. It's over 2.5 times as strong as the Falcon Heavy. It's a spacecraft with 7 engines on top of a booster, named Super Heavy, with 31 more Raptor engines. It's capable of carrying over 100,000 kilograms of material not only into low Earth orbit, but to Mars as well. If a base is set up on Mars, it could refuel, and then go even further than that. With the BFR comes Starship. It's just the top part of the BFR. Instead of putting payloads in orbit or sending us on deep space missions, it can also be used for travel on Earth. Starship is a system that will bring some of the shortest travel times humanly possible. You will be able to reach anywhere on Earth in under 1 hour. Imagine the commercial uses for this. You could work anywhere in the world and have a commute shorter than you would today. You could order a package and have it sent to you from across the world in hours. Visiting friends and family would be easy, and the term long distance starts to lose its meaning. The designs of the BFR change year after year. When working on revolutionary ideas, chances are you're not going to get it right on the first try. Historically, SpaceX is the biggest example of that. But when you realize that the Starship itself is more powerful than the Falcon Heavy, the advancements in rocket technology will start to become apparent. With spaceflight, reusability is the only way we could ever even think about leaving Earth and venturing anywhere else. Without it, costs will remain too high, and the dreams of going anywhere else but here will remain just that, a dream. But SpaceX are the ones leading the charge. They're the ones who are tackling the problems that nobody else will. While governments across the world push their space agencies to the sides, private companies will rise up. These are the ones who are building the future of our species. These are the ones who are reigniting the interest of space travel in everyone's minds. And these are the ones who will fill in the gaps and go even further beyond what anyone else in the world is doing. If you're uncertain about the future of SpaceX, I think we should just look back at Elon's previous ventures. SpaceX's missions and their reusable rockets will impact space travel the way PayPal affected monetary transactions, the way Tesla impacted electric vehicles, and the way Neuralink will impact our biology. 15 years ago, everyone was skeptical about SpaceX being able to even launch a rocket. But they did. People were skeptical that they'd ever be able to land a rocket. But yet, they did. Even recently, people doubted that the Falcon Heavy would work, but, of course, it did. 10 years ago, they had just gotten their first rocket into orbit. Fast forward to today, and they're making their mission statement a reality. So looking at the plans of SpaceX, there's a good chance that you're looking directly into the future as well. In 2015, SpaceX, for the first time, landed the first stage of the Falcon 9 back on Launch Pad 40, but directly adjacent to that is Launch Pad 39A. It's also owned by SpaceX, except the story behind it is what gives me faith. On my birthday, July 20th, in 1969, men first stepped foot onto the moon and changed the world, our species, forever. Just 4 days earlier, at 9:32 a.m., they loaded aboard a Saturn V rocket and launched into space. They had left Earth on a mission that no one else had ever done before them. But once the smoke and dust from the launch pad had settled, there lied Launch Pad 39A, the same launch pad that SpaceX is using today to launch the biggest and most powerful rockets ever made. The mystery of human existence lies not just in staying alive, but in finding something to live for.
As of lately, it seems that everybody is trying to tell you when and how the world will end. Some scenarios are far more familiar and likely than others. Those that are widely discussed in the media range from infectious diseases to nuclear war, all the way to collisions with massive asteroids. While they are all vastly different from one another, they all share one thing in common. They are all able to effectively end the human species once and for all. But all of these scenarios fall short when compared to one thing: black holes. We're all familiar with them, but what exactly is a black hole? Black holes are regions of space where the gravity is so high that the fabric of space and time has curved back on itself, taking the exit doors with it. But what does that even mean? And why are black holes black? Well, any large object, such as a black hole, star, or planet, has a certain escape velocity that is needed to escape the pull of gravity on that object. For example, Earth's escape velocity is about 11 kilometers per second. Move that fast, and you can escape Earth's pull and fly off to the edge of the universe. But chances are you'll probably be pulled in by something's gravity eventually, but that's not the point. The stronger the gravity an object has, the higher the escape velocity is. Now, black holes have some of the highest gravitational pulls in the entire universe. In fact, black holes are theorized to have singularities where gravity pulls you with infinite force, but we'll get to that later. Let's say somehow we made a black hole with the same exact mass of Earth, about 6 times 10 to the 24 kilograms. Alright, this looks good. Except this isn't to scale. It would look something more like this. In order to turn Earth into a black hole, you'd have to crush it down to about the width of your pinky finger, about 9 millimeters. So these two massive objects have the same exact mass, except one is the size of your finger and the other is the size of a planet. So how does this happen? When black holes are created, they are typically formed by the death of massive stars, those with about 20 to 30 times the mass of our Sun. While living, stars undergo nuclear fusion in their cores, fusing together lighter elements such as hydrogen and helium. This fusion of elements creates energy and pressure that pushes out away from the Sun, while gravity keeps the star held together. But as time goes on over billions of years, stars begin to run out of these lighter elements and move on to heavier ones. They begin to fuse together denser elements such as carbon and oxygen all the way up to silicon and iron. Except here lies the problem. Iron can't fuse with anything. There isn't any more energy being produced, so the power of the star's gravity takes over, collapsing the star under its own weight until it explodes in what we call a supernova. The outer parts of the star fly hundreds of thousands of miles into space, while the core continues to collapse under its own weight and becomes densely compressed. Remember how Earth has an escape velocity of about 11 kilometers per second? Well, if after all that, the core of what was the star is still massive enough, about 2.5 times the mass of our Sun, and dense enough, the escape velocity of the core becomes much greater than the speed of light, over 300,000 kilometers per second. This forms what we know as a black hole. An area of space is created where nothing, not even the fastest thing in the universe, light, can escape. But let's have some fun with it and dive into one. Imagine, just for a moment, that you are aboard a spaceship, but not any normal spaceship, one that can defy physics. One that can accelerate you to any extremely high velocity, even higher than the speed of light. This is completely impossible, but it's okay. Because you know your spaceship can reach any speed imaginable, you have no fear of black holes and decide to fall into one in the quest of science. You choose the supermassive black hole at the center of the Milky Way galaxy, Sagittarius A star. This behemoth of a black hole is over 88 million kilometers wide, nearly 100 times as wide as our own Sun. A black hole of this size will give you enough time to observe it as you fall into it. At first, things might actually be peaceful, and here's why. Because of the black hole's size, at this point, the gravity isn't exactly going to be painful for you, but it will have a noticeable effect on the light coming from behind you. As you fall towards the black hole, you notice some unusual things. First, the stars behind you as you fall into the black hole begin to grow much brighter. The light from those stars is being pulled so strongly by the black hole's gravity that they begin to blue shift. As you fall further and further towards the event horizon, that is the point where our universe and the inside of the black hole meet, it begins to take up more and more of your field of view. It's almost as if the entire sky in front of you is filled with darkness. As you're about to cross the event horizon, you see the rest of the observable universe condense into one single, minuscule point directly behind you. If you were able to zoom in with your telescope onto this point, you would see the light from all the stars and the galaxies in the universe, but you would also see a very dim red glow. You remember this? This is the cosmic microwave background, or CMB. It's essentially a map of the electromagnetic radiation left over from the Big Bang, the very instant that the universe came into being. The dim red glow you would see is actually this radiation being boosted into the visible spectrum. And then, finally, it goes dark. You have crossed the event horizon, and it's only darkness from here on out. You realize that it's time to get to work before you get ripped apart by the black hole's gravity. So you begin to observe, except you don't see anything. There is no light. The view out of your cockpit window is completely and literally black. There is nothing to see. There's nothing to observe. You began this journey to dive deeper than any human could into a black hole to discover what truly lies there. But there is nothing. You know the singularity of the black hole lies ahead, where our physics and mathematics fail, and you came to figure out why. But you can't. The answers are right in front of you, but you have no way of observing it. Your journey has come to an end, and it's time to leave this black hellhole. You attempt to turn your spaceship around and thrust away from the black hole at speeds not even light can match. But there's a problem. Your spaceship's instruments that are designed to detect the flow of gravity so you can orient yourself aren't exactly working the way you expected them to. They're supposed to be pointing you in the direction of the singularity, allowing you to turn directly around and escape, except they're indicating that the singularity lies all around you. In every direction imaginable, gravity seems to increase. Up, down, left, right. 360 degrees of nothing but stronger and stronger gravity. The point that you are currently at is the weakest that gravity will be for your future self. Every direction points further and further towards the singularity and your inevitable death. Clearly there's a problem with your instruments. This can't be true, can it? Except it is. It is true. Once you cross the event horizon of a black hole, there is no leaving. The three-dimensional coordinate system that we use in our universe doesn't work. Time does not flow similar to the way we experience it here in the normal universe. Time flows downwards, towards the singularity. The curvature of space-time inside the event horizon. Every direction that is theoretically away from the singularity would ultimately carry you backwards in time, into the past. This is the true definition of an event horizon. Once crossed, there are zero. Literally 0 points where there are trajectories that face away from the black hole. There are only trajectories that pull you in deeper and deeper. The singularity is all around you, and it is getting closer.
The entire universe, every electron, proton, atom, every star and galaxy, was born out of a singularity that brought about our whole existence. The Big Bang, an isolated moment in space and time, created something out of nothing. For eons we didn't know much about the universe, but through advancements in science and technology, we're now able to travel back in time, right to the point just after the Big Bang to finally piece together its entire story.